welcome everyone. I'm very pleased to welcome and introduce Sam Barron, who's an associate professor of philosophy at the Australian Catholic University. I believe this is in Melbourne, right?
Yeah, it's multiply located, but I'm in Melbourne.
Oh, I see. Okay. So Sam is on the Melbourne campus. Sam works on metaphysics and philosophy of science, on time and the philosophy of mathematics. He has won several huge grants from the Australian Research Council and has published in many of the top journals in philosophy. Today, he will be speaking about approximate space-time functionalism. So please, Sam, go ahead.
Thank you very much, Chris, and thanks again for having me to give you a talk today. I really appreciate the opportunity. All right, I'm just going to jump straight into it. All right, so I've got two aims today. The first one is to raise a kind of challenge for space-time functionalism. A little bit of autobiography. I initially set out to write this paper to sort of give an account of space-time functionalism that solved this challenge. And this paper is more or less a sort of tale of my failure to do that. So what I'm going to do after I raise this challenge is suggest a way forward. And suggest, I think, is going to be the operative term. I'm not going to fully develop it. All right, I'm going to begin with some background. So I'm going to tell you a little bit about the way that I'm thinking about space-time functionalism, but also one of the things that motivates some of the people who are interested in space-time functionalism to adopt the view. And then I'm going to, in the course of that, tell you a little bit about approximation and approximate realization and why that's a kind of important thing to think about when we're thinking about functionalism. One of the things that I'll then do is look at some accounts of approximate realization. So approximate realization is this thing that you kind of need to do when you don't have an exact realizer for your functional role. And this happens quite a lot. And it would be nice if we had a kind of story about what to do when you don't have something that exactly satisfies a functional role, but you can sort of find something close enough, which I think is something that we want to do in the cases that I'm looking at. And I'll look at some accounts of that and I'll become sad, at least for dramatic purposes, and then give you a sort of different way forward after that, where we're not going to think in terms of space-time functionalism in general, but rather something a little bit more local to do with certain functions that space-time performs and in particular location. And as we'll see, this may just be the view that Chris has that I've been struggling to understand. So we'll see what happens. All right, so a number of approaches to quantum gravity seem to signal the loss of space-time at some level. So there are sort of different, I think, traditions at the moment, let's call them that, but maybe they've progressed that far, exploring the notion of space-time functionalism. There's sort of one that arises in just straightforward quantum mechanics, where people are talking about a particular approach to quantum mechanics, namely wave function realism. Some people have explored it over there. There's also just some people interested in it in the context of general relativity, trying to understand what space-time is in that theory. But the kind of focus that I've got is on quantum gravity and attempts to reconcile general relativity and quantum mechanics to produce a unified theory. And there's a few different suggestions about how we might produce such a theory. We don't have anything like a complete theory of quantum gravity at the moment. But a lot of these approaches seem to suggest that you're going to lose space-time at some level, or lose spatiotemporal properties at some level. Exactly what level, exactly what that means, I think a lot of that's up for grabs and up for discussion. I think by now we've sort of seen this in quite a few theories. Loop quantum gravity and causal set theory are often focused on, but also canonical quantum gravity with this sort of infamous timeless Wheeler-DeWitt equation, which also sort of seems to not have any time in it, at least. And even in string theory, we might lose space, if not space-time. Now, one particular issue that arises from this apparent loss of space-time is what we call the problem of empirical incoherence, or the threat of empirical incoherence. And the worry is that on the face of it, if you lose space-time, you may lose the capacity to provide meaningful confirmation for your theory. So here's a sort of statement of empirical incoherence that is quite common in the literature. A theory is empirically incoherent if its truth undermines the empirical justification for it. So the basic idea is that if you lose space-time, and space-time is the thing that you need to provide the basis for empirical confirmation, then if a theory sort of implies that space-time doesn't exist and you need it to confirm the theory, then the truth of the theory is going to undermine your capacity to justify it. Or if you're going in the other direction, if you manage to justify the theory, you also manage to show that the theory is false because your method of justification presupposes something that the theory says doesn't exist. So here's a couple of statements of this. So we've got one from Nick Huggett and Chris Frutrick. They say, thus goes the worry, if a theory rejects the fundamental existence of space-time, it is threatened with empirical incoherence because it entails that there are fundamentally no local beables situated in space-time. But since any observations are of local beables, does not it then follow that none of our supposed observations are anything of the kind? In another paper by Vincent Lamb and Chris again, we've got a similar statement of it where they say, indeed, if space and time are necessary preconditions of theory confirmation in empirical science, then any theory denying the fundamental existence of space-time undermines the very possibility of its own empirical justification. Consequently, such a theory would seem empirically incoherent. So we've got these theories, they don't seem to have space-time in it, and in them, and that seems like a problem on the face of it if you want to try and confirm one of these theories. It's kind of an interesting problem because we have no idea how we could even empirically confirm some of these theories in the first place. But if we were to try, it seems like we would fail in a certain deep sense. So this is where space-time functionalism comes in. One of the purposes of space-time functionalism is to provide a kind of solution to this problem of empirical coherence. So the basic idea is, I think, a very familiar one in philosophy, and that's to say that the thing that has gone missing turns out to be there all along. It's just being functionally realized by something in your more fundamental theory. So, we've got this in the philosophy of mind. We want to try and find mental states in the world, but we look around and all we seem to have are these squishy brain states. But what we can do is we can sort of give a functional characterization of what it is to be a mental state and then say, well, look, these brain states play that kind of role. And so we get to say that they are mental states. And so we've found sort of a naturalistically acceptable notion of mentality in the world. Here, we're obviously not trying to do it for mental states, but the broad game is the same. We're trying to find space-time in some of these fundamental theories. And so what we do is we provide a functional characterization of what it is to be space-time, this sort of notion of the space-time role. And then we look into one of these theories, like into loop quantum gravity or into causal set theory, and we find something in there that gives us some confidence that the space-time role is being played. Usually this is sort of relying on certain kind of mathematical procedures that show us that you can kind of define up some metric structure from something that doesn't seem to have any. If space-time is functionally realized, then it exists. At least I'll assume that for the purposes of today. And so if you can functionally realize space-time, then you get to avoid this problem of empirical coherence, because the thing that you need for empirical confirmation turns out to be there all along. So that's the sort of motivation, and that's a nice, neat picture. There are, as I sort of indicated at the beginning, various versions of space-time functionalism on the market. I'm going to focus on the version that Vincent Lamb and Chris Frutrick put forward, which I've already sort of framed things in this way anyway, which is modeled closely on functionalism in the philosophy of mind. I mean, I think all of the kinds of functionalist proposals that have been put forward are descendants of functionalism in the philosophy of mind. But I think that this version of functionalism is sort of most directly keying into that literature and that debate. And so for them, this is how we should think about functionalism. We should think of it in two steps. First, you find the high-level properties or entities which are the target of reduction, or the thing that you're trying to find or locate in a more fundamental theory, and you give them a functional characterization in terms of their causal or functional role. In this case, it's not going to be a causal role, it's going to be some other kind of functional role. There's a little bit of, we can have a little bit of a debate about whether you can have sort of non-causal functional roles, but ultimately I think you can. So I'm just going to concede that for the moment. And then once you've got that functional characterization, you find something in another theory and that can play the relevant functional role. Now I want to sharpen this up a little bit in a way that I hope won't be too unpleasant. So what I'm going to do is I'm going to understand functionalism in terms of Ramsification. So this is the procedure of producing a Ramsey sentence for a theory, and this is usually how you would carry out that first stage of that functionalist project over in philosophy of mind. And then when you're carrying out the second stage, what you're looking for is something that satisfies the Ramsey sentence. So I'm going to tell you a little bit about Ramsey sentences, and then we're going to talk about space-time and Ramsey sentences as well. So here's the basic idea behind Ramsification. It's not that, I mean, you sort of try and read the stuff on Ramsey sentences and it can make you go a bit cross-eyed, but I actually don't think it's that nasty in the end. The basic idea is that you start with a theory. So you're always looking at theories in the first instance, and you look into your theory and you make a distinction between two kinds of terms. They have various names, and the terminology here is a little bit contentious. They get called by Lewis the sort of T terms and the O terms. You can think of those as the theoretical terms or versus the observational terms. Some people talk of them as the like troublesome terms, the things you're trying to get rid of, versus the old terms or ordinary terms, things that you're happy with. It doesn't really matter to me what we think of these terms are, as long as we can draw some kind of distinction. Each T term is going to be defined in terms of some O terms. And I'll give you a very simple example of this in a sec. And then a Ramsey sentence is just produced by replacing your T terms with variables bound by quantifiers, right? So you take your sentence describing some property or some feature of a theory in terms of some other features, and then you're just going to strip out the feature that you're interested in and replace it with an existential quantifier. And that existential quantifier gives you a kind of generalized sentence, which you can then take to another theory and see if something satisfies the sentence. And if something satisfies the sentence, if you can find some n-tuple of entities that satisfies the sentence, then you get to say that the functional role is realized. So here's a very simple example. Here's my simple pain theory. Pain is caused by pinches and punches and causes yells and yelps. Of course, it's not a complete pain theory. The Ramsey sentence is just strip out pain and quantify into that place using an existential quantifier. And then you can go, is there a neural state that can be substituted back into that variable to produce a true instance of the sentence? If yes, then you found pain. Good job. All right, so if we're going to extend this broad procedure over to space-time, and in fact, if we're going to talk about space-time functionalism at all, I think we have to have a theory in mind. I'm inclined to focus on general relativity because I take it to be our best theory of space-time. And I think I'm not alone in focusing on this particular theory. I think that there are space-time functionalists who aren't obviously thinking in terms of general relativity in the first instance, and I'm not entirely sure what to say about them, but we can have a chat about that later on if you're interested. And I think there's good reason to focus on general relativity because, as Chalmers says in this quote, it's sort of where this theoretical concept seems to have come from, right? Like we have a concept of space-time because it sort of got introduced into relativity in the first instance. And so that seems like a good place to start for providing a functional characterization of this beast. So how are we going to do that? Now, I'm going to say a bunch of stuff that's probably quite controversial. Ultimately, it's not going to matter too much if what I say is right, except in one key respect, which I'll talk about. Full disclosure, providing a Ramsey sentence for general relativity is not a pleasant experience. I don't really recommend trying to do this. But what I've done to make this a little bit easier is try to simplify it a little bit. So what I'm going to do is I'm not going to try and Ramsify general relativity overall, like the entire theory, because I think that's going to be quite hard. What I'm just interested in is space-time in the context of that theory. And so I'm going to treat space-time as the T term, the thing that I'm going to have as the target for my Ramsey sentence. And I'm just going to treat space-time as a set of physical elements that can be represented by a differentiable manifold equipped with a metric, where the metric is defining the geometry pointwise, and it's the thing that you get out of the field equations, roughly. What I'm going to do is I'm going to get the Ramsey sentence, because I have to talk about a set of elements. I kind of need a way of talking about the elements. I'm going to use plural quantification. That's just what that E-XX is. It's not that important how we do this with respect to the quantifiers, so long as we can quantify into the scope of the set. And so here's my proposed Ramsey sentence. There just is something that such that a set containing it is isometric to a manifold equipped with the metric tensor field that you get from general relativity. You kind of can't do the same thing in pain where you said, look, pain is just this thing that blah. You have to sort of talk about set containing these objects because general relativity is this big chunk of mathematics. And so your sort of best grip on what space-time is this being represented by this object, this mathematical object. And so that's why I've sort of defined it in this way. As I said, we can have a debate about whether this is the right Ramsey sentence or even the sort of right partial Ramsey sentence for space-time in this theory. It won't matter for my purposes too much, so long as isometry to that metric field is part of the story. If space-time functionalism in some sense says that partly what it is to be space-time is to involve this metric thing in general relativity exactly as described in general relativity, then that's going to be enough, I think, to motivate the version of functionalism that I'm going to describe now. All right, so just going to grab some water. So as I said, what I'm interested in is approximation, because I don't think that when you start looking into the theories that we might be interested in finding space-time within, that we find anything that is exactly this metric structure that you have in general relativity. And so I've got a couple of indicative statements with respect to a couple of these theories. So in loop quantum gravity, as Ravelli says, what you can do is you've got this mathematical construction which allows you to define up something over a spin network, kind of sort of distance and volume operators over a spin network that enables you to get something that approximates the metric structure of general relativity at certain energy scales. You're not going to get anything that is exactly that metric structure. At best, you get this sort of approximation relation. And I think there's a good reason for that, which I'll talk about in a sec. The other case is causal set theory. So in causal set theory, you've just got this fundamental structure of a partial order over some things, whatever those things might be. And then you've got these results that say that with certain sorts of partial order structures, you might be able to get space-time structure coming out, metric structure coming out. But at best, what you can do is you can define up a kind of mathematical procedure for converting these causal set structures into a manifold structure that is approximately isometric to a manifold equipped with the metric tensor field. Again, you're not going to get something that is exact. And the reason for this is that these fundamental structures are discrete, the metric tensor field is continuous, and it is hard to get a structure of discrete objects to exactly mimic the continuous structure of a differentiable manifold. So you end up getting something that's near enough. In the case of loop quantum gravity, it looks a lot like the Reggie calculus. If you're familiar with that, what you can sort of do is you can build via triangles this thing that looks a lot like a metric, but is not exactly continuous because it's got some jumpy bits in it. All right, so it looks like space-time is not exactly realized, at least given that you don't have the exact metric structure of general relativity appearing in these fundamental theories. It's approximately realized. I mean, you've got these approximation procedures in a couple of these theories. So it's not like you don't have anything like space-time in there. You've got something like it. And this is not at all unusual for functionalism. Depending on your theory of pain, it's pretty likely that pain is at best approximately realized as well. In fact, I don't really know of a sort of functional kind where we've completely nailed down theoretically what the functional role is such that we can then go out and find something that exactly satisfies it. Almost always in functionalism, we're looking at things that are near enough. Now, I'm totally happy with the idea in principle that space-time is sort of realized well enough to be able to say that it exists, right? So there's a sort of, close enough is good enough, fine. The issue that I have is that it would, and this is sort of where I got to in my thinking. I wanted to develop that kind of view and spell out the conditions under which near enough is good enough in the case of space-time, so that we can sort of better understand the exact sort of functional relationship between things in these fundamental theories and the metric structure of general relativity. But the sort of stumbling block I hit is that you need to specify some conditions under which you're allowed to say that something is realized, even though it's not exactly realized by an underlying theory. After all, we're talking about approximation, we're talking about a similarity relation between whatever it is that you find in one theory and the structure in another theory. And that thing is a vague little guy, and you need to be able to pin it down a bit in order to be able to specify when you are and are not allowed to say that functional realization has occurred, given that you don't have exact realization, but you just have sort of near enough. And specifying the conditions under which near enough is good enough is what I want to do in the second part of the talk. And that's the thing that I spectacularly feel like I failed to do. Now, what's nice is that Lewis saw this coming in the paper where Ramsey sentences really first get applied to mental state terms. He gives you some conditions for approximate realization. And these are the conditions that he gives. He says, look, when the functional role specified for a Ramsey sentence is not exactly satisfied, this is not a quote, by the way, this is my reconstruction of what he says. He says that we can still say that the T terms in your theory, the things that you're functionally analyzing, are functionally realized so long as you've got another theory, T prime, which can be obtained by slightly modifying your original theory. And that is more or less a direct quote, such that that second theory is implied by the first theory, but not vice versa. So you don't have mutual entailment. You've just got sort of one-way entailment from one theory to the other, and you can get there by slightly modifying the theory. And the Ramsey sentence for that modified theory is exactly satisfied by something in another theory, right? So basically, so long as you've got a way to like break off the bits that aren't working from the original theory to produce another theory that is entailed by the first theory, and that theory gets exactly satisfied, then you get to say that the T terms in the first theory are in fact functionally realized after all. So, if the first theory is your theory of pain, and then you modify that to come up with something that is like sort of pain star, and that thing gets exactly realized, then you get to say that pain is functionally realized after all. I'm not overly fond of Lewis's way of putting it, to be honest. And part of why I'm not fond of it is because I'm not entirely sure how to apply it in the case of quantum gravity that I'm interested in. It's not obvious that there's a way to slightly modify general relativity to produce another theory of space-time that is exactly realized in quantum gravity. Maybe this can be done. I'm not totally sure. I think the best bet is something like the Reggie construction, which is a discrete attempt to sort of discretize the general relativity. But even then, you're not coming up with anything like a discrete set of field equations that are entailed by the original theory, which is what Lewis's condition would require. I think that, and more generally, I just think that this account is too demanding. I think that we want to be able to say that something in a theory can be realized well enough by something in another theory, even when there's no mediating theory, even when there's no sort of theory in between that gets exactly satisfied. We want to say it because the sort of like ontology looks close enough between the two theories, even if there isn't some other third theory that is getting the case exactly right. So I think Lewis's picture is a little bit too demanding. Not much of what I have to say relies on rejecting Lewis's picture. If you're fond of Lewis's picture, then you can run with it, and I think you'll get into the same trouble that I get into in a minute. But what I'm going to do is I'm going to replace this because I don't like it. So what I'm going to do is I'm going to replace it with something that looks a little bit nastier, but I don't think the idea is that complicated. So these are two conditions under which Ramsey sentences get satisfied. So these are two conditions for functional realization. The first condition is just the case of exact realization. So I've just put it in there to give you a complete set of conditions. What that's saying is, look, if you've got some interval of entities and the entities exactly realize the functional role specified by a Ramsey sentence, then the T terms are realized by those objects. The T terms just are those things. If there is no such interval that exactly realizes the functional role, but if there's an interval of entities posited by some other theory, and that interval is sufficiently similar to whatever would exactly realize the functional role, then you get to say that the T terms are functionally realized after all. So, you've got a theory like general relativity. You look at, you've got this functional characterization of space-time. You look at a theory like loop quantum gravity. There's nothing in there that exactly satisfies that functional role, but there are some objects that are like really similar to what would exactly satisfy it if it existed, right? So you've got something that's really similar to a kind of continuous metric structure of space-time, but it's not exactly the same thing, but it's close enough that you get to say that functional realization has occurred, and you don't have to have this mediating theory. So I've cut out the middleman. And so here's just a graphical representation of what I've done. Lewis's theory has got this entailment relation between these parent theories up the top, and then a functional realization coming from the bottom from this third theory. And I've cut that guy out, and all of what I'm doing is about the similarity relation between the objects that satisfy functional roles, whatever those might be. Of course, the issue with what I just gave you is that it's got this similarity notion in there. And I think what we need is an account of what that similarity is. So it's not like I've just given you a set of conditions that gets rid of that similarity. I was just trying to sharpen up the demand for similarity in the first place. And we need to give an account on my picture of when the sort of objects in some fundamental theory are sufficiently close to exact realizers to be able to say that they realize the thing that you're interested in. I think the same question arises for Lewis. He says that a theory has to be a slight modification. How slight is slight? How similar do the theories need to be before you can give an account of when sort of approximate realization occurs? So it's not like Lewis is getting away, it's not like I'm introducing the problem by modifying Lewis's conditions in this way. I think the problem's there for Lewis already. And I'm going to look at some ways of supplementing my story to give these kinds of similarity conditions. They will work for Lewis if you tinker around with them as well. So if you prefer Lewis's picture, everything I'm about to say can be done with that as well. All right, so I'm going to start. I'm just going to go through some options now. This sort of chunk of the talk is, here are some ways we might account for the similarity between theories or the objects in theories in order to be able to say that something like space-time is realized well enough. And I'm just going to sort of play the game of showing that these just don't work. If you can come up with some better ones, I am all ears. So the first one, and I think that this is a kind of obvious one to try, is to think in terms of empirical equivalence. So you might look at two theories and you say, okay, well, when are the objects in one theory sufficiently close to the objects in another theory to be able to say that functional realization has occurred despite there being no exact realization? Well, so long as the two theories carry all of the same empirical predictions, then the ontology of the one theory is just close enough to be able to say that you've got some functional realization happening. So I've sharpened that up on the slide into a more exact condition about every sort of confirmed empirical prediction of the theory you're trying to functionally realize also being a confirmed empirical prediction of the theory that manages to carry the entities that do the functional realization in the end. So I think there are some obvious difficulties with this. I think that the account just massively misfires because there are lots of pairs of empirically equivalent theories where we just don't want to carry out a functional reduction of this kind. So here's a toy case. Think about the relationship between quantum field theory, special relativity, and Lorentz's ether theory. So these three theories stand in the following relationships. Lorentz's ether theory and special relativity, I mean, if you do a little bit of work, you can get those theories to be empirically equivalent in the sense that they make all the same empirical predictions. But of course, one theory's got this ether in it permeating all of space, whereas the other one doesn't. all of the confirmed empirical predictions of special relativity are confirmed empirical predictions of quantum field theory, because quantum field theory just has kind of special relativity slotted into it in a certain sense. And so all of the confirmed empirical predictions of Lorentz's ether theory are also confirmed empirical predictions of quantum field theory, because after all, they are no different from the empirical predictions of special relativity. By the very condition I laid down, though, what that means is that the ether in Lorentz's ether theory, if you functionally analyze that, that thing is going to get realized in quantum field theory as a result, merely in virtue of the overlap in empirical predictions. Because after all, the condition was just, so long as these two theories are empirically equivalent, then the ontology of one can functionally realize the entities in the other. And because, or more specifically, because the empirical predictions of one are recaptured by the other, then the ontology of one can functionally satisfy the other, the functional terms in the other one. And so you end up in this situation where these unobservable entities like the ether get functionally realized just because of this overlap of empirical predictions. You know, nothing in quantum field theory exactly realizes the Ramsey sentence for Lorentz's ether theory, but if all it takes to be close enough is to carry the same empirical predictions, then you kind of can't stop the ether theory from getting realized in the underlying quantum field theory. And that just seems like the wrong result. There's a sort of general problem coming up, I think, which is that you can just keep cooking up theories to smash these conditions down. And it's not hard to cook up weird theories. So, you know, I just gave you the case using quantum field theory, special relativity, and Lorentz's ether theory. But of course, I can just take general relativity and I can just add an ether to the theory as a sort of extra metaphysical posit, and just stipulate that it's in there and that it does no empirical work, just like the ether theory and Lorentz's theory. You know, the sort of the empirical content, the laws in Lorentz's ether theory sort of conspire so that you can't detect the ether. You could just do the same thing in the context of general relativity to come up with this other theory, which I'm going to call general relativity plus. And neither space-time nor this ether are functionally realized exactly in a theory of quantum gravity, but they're both, if they both have the same empirical consequences, then if space-time gets functionally realized, it's hard to see how to stop the ether from getting functionally realized in this sort of other weird theory that I've just cooked up out of nowhere. And I'm not saying it's a good theory. It's of course a terrible theory, but the point is that empirical prediction is too blunt of an instrument to rein in functional realization. And this is going to be the story from here on out. Whenever I tried to build conditions that would enable me to say that, you know, space-time is functionally realized because something is close enough in the underlying theory, it just turns out to be possible to cook up a theory that can where you don't want to say that functional realization has occurred, but the condition is satisfied nonetheless. So here's another option you could do. You could try and focus on explanation. So rather than focusing on empirical predictions, you could say so long as if you've got two theories, and in one theory, all of the explanations or all of the things that get explained can be recaptured within the explanatory structure of the other theory, then the theory that's sort of getting recaptured in that way, that theory is close enough to be able to say that functional realization has occurred. So whereas before it was, so long as the empirical predictions are recovered, then you can say that something is functionally realized. Here, it's so long as the explanatory structure, which may go beyond the empirical predictions, so long as the explanatory structure gets recovered, then you can say that functional realization has occurred. So, you know, for instance, in the case of loop quantum gravity, you don't have anything that exactly realizes the space-time structure, but if everything that general relativity can explain can be explained by loop quantum gravity, then you should think that there's something in loop quantum gravity that functionally realizes space-time well enough. That's the sort of thought. The problem is I can just keep messing around with this theory GR plus to make it functionally realized when I don't want it to be functionally realized. So I can just take GR plus and further stipulate that this thing that I added into it, the ether, does no explanatory work in the theory, at least no work that's not already done within general relativity. And the problem is that explanatory recovery provides me with no way to prevent the ether in this GR plus theory from being functionally realized in loop quantum gravity as well, right? Because this theory will be explanatorily equivalent to general relativity. And if all it takes to say that the things in one theory are functionally realized by the base theory is the explanatory equivalence, then I can get the sort of ether to get functionally realized because it's close enough by this measure. So another option that you might try, and this was just me trying things out to see if anything would work. Another option is, well, look, theories have counterfactual implications, and the counterfactual implications may go beyond the explanatory implications, and they may go beyond the empirical predictions that the theory makes. Which counterfactuals a theory supports may not have much to do with explanation or prediction, but nonetheless, you might be able to individuate theories in terms of their sort of counterfactual supporting structure. So I thought, well, what if you say that, so for loop quantum gravity, so long as every counterfactual that's true in general relativity gets to be true in loop quantum gravity, then you can say that space-time is functionally realized well enough in the underlying theory. Again, the problem is that I can just stipulate of the ether that it's counterfactually idle. You know, like I can just build this terrible theory which has this sort of metaphysical dangler in it that does nothing. It carries no empirical predictions, it carries no explanatory predictions, it supports no counterfactuals, but it's there. And so you can produce a Ramsey sentence for it in the context of that theory. And as long as the counterfactuals get recovered by some underlying theory, that thing gets functionally realized when you don't want it to be. And I've tried more than just the options I've given you. I'm going to go through a couple more because they are sort of relatively important once we're starting to think about functional realization more generally. So another one is to try and recover one of the things that I disposed of in Lewis's conditions. So one of the things I took out of Lewis's conditions because I didn't like it was implication between theories, because I thought, who knows if we've got a theory that is implied by general relativity that can be fully satisfied by some more fundamental theory. But you might try and put it back in, and you might say something like, look, if general relativity can be derived from, say, loop quantum gravity, then we should think that the entities in loop quantum gravity are sufficiently similar to the entities in general relativity to be able to say that space-time exists, right? So this sort of deducibility requirement now is carrying the power of the functional realization. And I mean, this sounds sort of initially workable, but the problem is that it's not at all clear to me that general relativity is going to be a logical consequence of quantum gravity in this sense. So what we've got are sort of various approximation procedures which allow you to derive, in a loose sense of derive, I think, the way that people use this term, people like Butterfield and Isham, when they talk about derivability, they're really talking about the kind of approximation procedures that I was pointing to earlier on, when you can do things like define up kind of mathematical procedure for coming up with something that gets you numerical results that match some of the solutions to general relativity quite closely. But deriving the field equations from loop quantum gravity, it hasn't been done. I guess it would be nice, but it's not at all obvious to me that we're going to be able to do this. So I just don't think it's going to work. There's a sort of more sensitive version of this, which is, instead of focusing on implication between theories, you focus on a kind of mathematical approximation relation. And you say, so long as you can sort of, use those very approximation relations that I was pointing to in the case of loop quantum gravity, and use those as the basis for your functional procedure. You say, look, as long as you can sort of mathematically approximate to a sufficiently high degree general relativity using something like loop quantum gravity, then you should think that the things in general relativity are functionally realized by this underlying theory. The ontology of the underlying theory is close enough. And the problem here is that mathematical approximation is just another similarity relation. And so it just feels like we're back to square one in some sense, because if we want to start talking about how the mathematical structure of one theory approximates the structure of another theory, there are lots of ways that you can think about approximation. So for instance, Butterfield and Isham say that X mathematically approximates Y roughly when, by neglecting certain quantities or ignoring certain degrees of freedom, we can produce the mathematical structure of Y exactly. So, right, so chuck some stuff out and the field equations pop out. I mean, the question is, which quantities and degrees of freedom do do you hold fixed and which ones do you neglect and allow to vary in order to say that the mathematical approximation is sufficiently close to be able to allow for the functional realization to occur. Because of course, you know, if you can chuck out enough stuff, the mathematical procedure is completely trivial, right? So you have this question about how much you're allowed to approximate the underlying mathematics in order to say that functional realization has happened, but then that just is another kind of similarity relation that we need an account of. So this is the point that I got to. I'm like, well, I can't obviously specify these approximation conditions in terms of empirical recapturing, explanatory recapturing, counterfactual recapturing, deductive terms in terms of like straightforward logical consequence, or even these mathematical approximation terms. And at that point, I'm just not sure how else to do it. And the problem is T terms for unobservable entities, because when you've got unobservable entities kicking around in your theory, then, and you know, unobservable in a really deep sense, in the sense that they're not just not making empirical predictions, but they're not explaining anything, and they're sort of counterfactually idle as well, then it becomes really hard to stop those things from getting functionally realized once you've got a sort of near enough is good enough attitude to functional realization. We can just build weird theories with unobservables in them all day, and we'll end up with problems of this kind. So what I actually recommend doing as a result, so this is the sort of bit where I get sad, I recommend giving up space-time functionalism, at least as it's usually put forward as a kind of continuation of the functionalist project in the philosophy of mind. I don't know how to specify these approximation conditions in a way that makes the functionalist project work, but I also am not entirely convinced that you need to be able to say that space-time is functionally realized in order to be doing the kind of work that space-time functionalism was introduced to do. So remember, we brought in space-time functionalism in order to solve this problem of empirical coherence. We want to be able to say that theories like loop quantum gravity, despite maybe not having space-time fundamentally, nonetheless, these theories can be open to empirical confirmation or disconfirmation in a non-trivial way. And what I think we should do is, rather than trying to recover space-time in the full-blown functionalist sense that I've been looking at so far, where you sort of Ramsify a theory and try and find something that satisfies the Ramsey sentence either exactly or near enough, we should instead just focus on particular functions that space-time performs and try and get those to get realized in the underlying theory. So in a slogan, functions, not functionalism. Actually, the view is going to be a form of functionalism. So that's not a particularly apt slogan, it will turn out. So I'm going to sharpen the picture up a little bit by focusing on one function in particular, and that's the function of providing locations for objects. Because after all, the problem with empirical coherence is that without space-time, it looks like we don't have a structure in which things can be located, and having things located looks like what at least a necessary condition on empirical confirmation, gathering empirical observations. I doubt it's a sufficient condition, but it's at least necessary. So what we can do, I think, is just focus in on location itself, independent of whether we're thinking about space-time, and say, okay, well, look, one of the things that space-time does is provide location. So let's just focus in on what I'm going to call the location function. And we're going to functionally analyze that thing. And then we're going to show that something can play the role of location in that sense in these more fundamental theories, even if it's not space-time. So I think this is a kind of functionalist view. I think it's functionalism about location rather than functionalism about space-time. Location is going to be based on whatever our best account of location in the context of empirical coherence happens to be. And I think a kind of outstanding project here that falls out of this discussion is that we need a theory of location. We need to understand location better in the context of empirical coherence particularly. How does location support empirical confirmation? What notion of location do you need? What minimal notion of location do you need in order to be able to say that that a theory is empirically coherent? I'm inclined to think that space-time, in the sense that we mean in general relativity, is surplus to requirements. You don't need anything as fancy as the metric structure of space-time in order to be able to have locations for objects that supports empirical coherence. And once we've functionalized location, given this theory of location, we can then see if something plays that role in these theories, like in loop quantum gravity, in causal set theory, in string theory, and whatever theory that you're interested in. So here are the advantages, I think, of going this way. You get to solve the problem of empirical coherence, which is what we wanted to do in the first time. You don't need to functionally analyze spacetime. So one thing I haven't talked about in a great deal of detail is that there is this consternation about what the spacetime role is. And I've just run completely roughshod over that by saying, I'm going to Ramsify general relativity, and I don't care if it's the right Ramsey sentence. There are some people who really do care about what this spacetime role is and about getting it right. And I just don't actually know how to carry out that debate in a fruitful way. I think that it's not obvious to me how we can settle disputes about what the correct functional analysis of spacetime might be. I'm not even sure how we can do that in the case of pain. I don't know how to do it in the case of spacetime. So I think you can just totally sidestep that debate. We don't care about spacetime, we care about location. Let's look for location in these fundamental theories. It also sidesteps another kind of problem for spacetime functionalism that I haven't talked about, but which I think is a kind of interesting problem. There's an objection by David Yates, which I'm going to call a collapse objection. And the idea here is that spacetime functionalism is often thought as a kind of reductive thesis, or functionalism in general is often thought as a kind of reductive thesis. In fact, I think the way that it was phrased initially was in terms of reduction. Reduction is often paired with a notion of identity. So when you manage to reduce something, you are identifying two things in some sense by some kind of theoretical identification. And what Yates says is, look, these theories that you've got, theories like loop quantum gravity, they're not supposed to have spacetime in them. That's sort of one of the things that we're interested in the first place, is the fact they lack this kind of metric structure. If you manage to functionally realize spacetime in the context of one of those theories, then in some sense you are in fact admitting that they have that kind of structure in them, because functional realization is a kind of identification. So you are just saying spacetime exists in the context of those theories. And he worries that that's flying in the face of the way that people are thinking about these theories, or the way that reason people are interested in these theories in the first place. If you're not trying to functionally analyze space-time, but you're just trying to functionally analyze location, you're not going to be in the position of saying that space-time has to exist in the context of these theories. You could discover it exists, right? And I think it's a genuinely open question as to whether these theories do eliminate all metric structure of this kind. You could still discover that they do in fact have space-time in them. But if you're just interested in location, you don't have to go looking for space-time. And that leads as a leads as a further point to 4, which is that we can allow for the possibility of eliminating space-time completely. And I mean, you might not like the idea of eliminating space-time for, scientific or metaphysical reasons. I think it would be really weird if we were to rule it out based on how we've set up our functional reduction. And I think that it would be nice if, when we're thinking about our functionalism, that we don't sort of rule this out by fiat. The position that I'm putting forward doesn't rule it out by fiat. It might be false, and it probably is false, but it nonetheless becomes a viable option, because location doesn't have to be space-time location. It could be location in some other sense, maybe some sense that we don't fully understand yet. What plays the location role might be some new kind of thing. And of course, the catch here is that we need a theory of location in general, and as it relates to empirical coherence, and I don't have such a theory. I think it's a worthwhile project to develop that theory, actually. I don't know exactly what context we should be thinking about that theory, because it seems to be something that is sort of linked to the methodology of science in a really interesting way, and I don't really know how to think about that. Okay, so I don't know that this is not the view that Vincent and Chris have in mind. So at one point, they do talk about functionally analyzing space-time. They have put forward this sort of functionalist picture, but at one point they say the following thing, which I find quite interesting. They say that they sort of get to the point where the rubber hits the road. They're trying to show in, say, loop quantum gravity that something really does play the space-time role. What they end up doing is just focusing on this thing called the localizing function. And they say the localizing function involves at its core the notions of coincidence and contiguity, the functional role of localizing a physical entity, what it means for a physical entity to be localized, crucially involves coincidence and contiguity relations. As a consequence, in schematic terms, the second step crucially involves how loop quantum gravity entities or properties can instantiate coincidence and contiguity relations in an appropriate context. This looks a lot like the picture I just gave you, I think, because the focus is not on space-time functionalism, but on location functionalism, or on localizing functions. And what they end up doing, I think, is showing that some meaningful notion of location is kicking around in loop quantum gravity, even if it's not the sort of full-blown metric structure of general relativity. So this may just be the view that they had in mind all along. I mean, I still think was worth it for me to get to a point where, like, if that's true, that it's worth it for me to get to a point where I understand that this is how the view is working. And it's also, I think, valuable to see that location is actually super important, and that space-time is less important than location. All right, so here's the summary. Space-time, unlikely to be exactly realized in quantum gravity, at least on the notion of space-time that I've given you, and we can argue about that notion of space-time. Approximate realization looks like the way to go. It seems like a natural thing to do. After all, that's what Lewis thought we should do when we hit this problem with functional realization generally. But then we start trying to specify approximation conditions, and I ended up tearing my hair out trying to do that, and I just don't quite see a way to do it. Maybe there's something I'm missing that's obvious. We can't clearly specify those conditions in empirical, explanatory, counterfactual, implicative, or mathematical terms. So let's give up space-time functionalism and revert to what I'm going to call location functionalism. Thanks, folks.
Thank you very much, Sam. Great. Okay. So we have a bit more than half an hour for discussion. As always, please write Q in the chat for a question and F for a follow-up or a finger. The first one is David. Please go ahead.
Thank you. Just a quick warning. I'm waiting for my landlord for an apartment tour, and they might arrive any minute. So if they come, I'm going to have to run. I'm going to try to make this quick. First of all, thanks for the wonderful talk. Very clear and fascinating. I'm wondering very basically what the reason is we should think that the space-time functionalist needs to worry about approximate realization. I take it the reason within the philosophy of mind is we have this kind of folk psychology of pain and mental states, and we also think there is something to this folk psychological theory. We want to preserve some of it. We don't want to walk around telling people everything you think is false. But we also know we have this much better scientific theory of mental states and of goings on in the mind and in the brain. And these sort of are in tension with each other to some extent. So one challenge is to show that, at least to some extent, approximately, the folk psychological roles are realized by the better scientific, by the better account, the naturalist account, whatever, of mental goings on. I feel like the situation here is quite different, right? Because of course we have in some sense, a super good theory that scientists use, GR, but we also know it's strictly speaking false. And strictly speaking, false just means false, right? There is no, so of course it is really useful in lots of regimes and we can do lots of good work with it. But one reason we're trying to look for a better theory is because we know that even in its own regime, it breaks down. So the space-time functionalist might just say, well, I don't actually want to realize the GR role, any role that's definable within GR. I want to give an account of a role that's realized in the better theory, which is going to be fundamentally a quantum gravity theory, and it is going to give us an account of our evidence. This account is going to be different than what GR gives us. It's going to be an account, in the quantum gravity context, it's going to talk about volumes and areas and things like that. But of course, it's not going to reproduce GR. And now in this new total theory, we're going to implement a functionalist project, potentially, where we say, oh, so we have these macro roles, and the macro roles are the ones that support our evidence, and those are functionally realized by the fundamental ontology. And they're exactly realized. So, and then of course we have a story for why the new theory we have in certain regimes approximates or is even exactly like our old theory, right? But in the key difference seems to be approximate realization is important in philosophy of mind because we want to hang on to the old theory. Here we don't, right? So I'm just wondering if that gets closer to.
I don't think I disagree with much of what you said, and I think that in some sense the picture I gave you at the end is quite sympathetic to that picture, because the picture I gave you at the end is like, let's just let our theory of quantum gravity tell us what location is like, but we still have some sort of conception of location that we need to be satisfied by in order to have empirical coherence, but we don't have to go looking for space-time in the GR sense, right? So I think I end up in a similar place. I think we can't do it exactly the way that we might want to do it, which is to say, take a theory of quantum gravity and just, functionally analyze the sort of space-timey thing in there, because on the one hand, we don't really have a complete theory, so it's not totally clear what it is that's even the target in that case. I mean, we can look at these fragments of theories, and maybe you can look at string theory, something like that. But also, so yeah, we don't have a total theory, but also it's not completely clear, I guess, that we want to just sort of get rid of GR completely. And one reason for that is because of the substantial empirical success of the theory. And is it false? I think this is not totally obvious to me. Like it doesn't give you a theory of everything, but like if you restrict it to a certain domain, it seems like it works pretty well for that domain. So I guess the thinking is we don't want to sort of junk it completely, and so that's what motivates looking for the sort of space-timey thing in the first place, because that's been quite good to us so far. But in the end, we may have to give it up in the way that I was suggesting, and maybe in the way that you're suggesting. Why does approximation matter? So I agree that the case is different to the philosophy of mind case. I guess I was trying to do what space-time functionalists want to do. And that's why I was taking approximation to be important, because if they really do want to functionally analyze general relativity, and at least some people seem to think that that's the way to go, then you're going to need something like this approximation relation. There are other functional roles that you could focus on, and then we could have a debate about which other functional roles might be important. But I think that there is at least some dialectical motivation for focusing on GR in the first place. Yeah, I mean, I don't think I disagree that much with what you're saying, though. Thanks.
Great, thank you. Ryan has a follow-up.
Yeah, I was just wondering why the fact that it's been good to us means we don't want to give it up. So, I mean, Newtonian spacetime was really good to us, and obviously, it seems like as philosophers, we more or less gave it up, even though, of course, in simple physics, you use it fine with no problem, and but we don't really worry about the ontology of it or whether it's functionally realized by GR or something.
So I guess some people do worry about whether Newtonian space-time is functionally realized. So I think there's some recent work by Ellen Knox and David Wallace actually in this direction, where they are sort of thinking about, whether sort of different notions of space-time, even Newtonian ones, might be functionally realized by sort of flattish regions in our world. Why? I mean, yeah, we can just sort of give up GR. I guess the thought is that whatever we recover, like whatever we go looking for, we want it to be able to capture at least most of the empirical stuff that supports general relativity. So it's a natural place to start to look for something that's like space-time, because it's kind of almost guaranteed from the outset to have the same empirical power as space-time itself, rather than trying to start from scratch and look for something completely new. So I think that's why the functionalists are thinking about space-time in those terms. And as I said, I think that some people might actually resist even the idea that we don't want, say, Newtonian space-time to be functionally realized.
Okay, great. Baptiste.
Right. Thanks a lot. I mean, I agree with a lot of things you said, and also in response to David and Ryan. So I think it's nice to use approximate realization. Now my question is at another level, right? Is it that worrisome, right? So, yeah, I guess you have to explain me something because why is it a problem that we can build a theory called GR plus, or let's say a class of ghost theories, right? They are ghosts because they're kind of there but not really. But so you seem to really take this as a problem, right? That if we accept approximate realization, then we have to accept that we have those kind of theories in the background, and we don't really want that. But I was wondering, is that really a problem? I mean, could we not just say that we have all those theories, but what we are really interested in to account for the theory that is on the market, GR, and it's not that big a deal that there are all those theories, right? So did I miss something about your reason to be really not liking those ghost theories?
So my beef is not with the theories themselves. Like I'm happy. Like I think there just are such theories because I think theories are cheap. You can build them. You can I did just invent those theories. Well, like I didn't invent them. I think other people have talked about these sorts of weird etheric relativistic theories before. I'm totally happy with the theories. What I'm pointing to is that we might not want to be forced to believe in the existence of the ether. And the point is that if near enough is good enough for functional realization in the case of space-time, right? So we don't have space-time exactly, but we've got something near enough which allows us to say, oh yeah, space-time exists. The conditions under which something is near enough to say that space-time exists turn out to be near enough to say that the ether exists on the conditions that I gave you. That makes them bad conditions in my view. I mean, maybe you're not unhappy with the idea that we say that the ether exists in some sort of I don't know, thin deflationary sense that you can take back, or some sort of insubstantial sense. But at least the problem that I was pointing to was not with the theories themselves, but with the content of those theories gets functionally realized when we might not want it to.
Right. Well, I guess I will react to that in two ways. So my first reaction will be, now I understand why you specify that you accept that the reality of space-time, right? You don't consider eliminativism, because if we have a form of eliminativist functional realization, then we don't have this problem, right? And then if I agree, if we have this kind of realist commitments, then we have to accept the existence of the entities posited by our functionally realized theories. And so we have to accept, in some sense, the existence of ether. But I would not think that it's that bad. It's not really a problem. I mean, if you say that ether exists and you give the relevant context of what you mean, namely that there is a realized theory, I mean, I guess I would be ready to bite the bullet. I mean, yeah, that would be my way to navigate that. And then I would say, well, I'm happy to bite the bullet, because then I can just use empirical equivalence and explanatory and other of the conditions you gave to say exactly what's going on. I mean, that would be my gut feeling about what's going on there.
Yeah, and I guess I am sort of showing my metaphysician stripes when I'm like, no, the ether can't exist. If you're happy with the existence of the ether, then I think you can just bite that bullet. I don't want to bite that bullet. I mean, partly why I don't want to bite that bullet is because it makes the existence of anything via functional realization kind of not very interesting, because it doesn't turn out to be a particularly great path to ontology in some sense, because it gets you things that I just don't think exist. I don't think there is an ether.
Right, but can I just a quick follow-up? If ether exists, right, it will exist in the sense that it satisfies a Ramsey sentence, right? And the Ramsey sentence will be very much alike another Ramsey sentence in another theory, right? So ether will exist in I mean, if you're a structural realist, for instance, something like that, maybe you could kind of weaken a bit the gap, right, between ether and another theoretical term, and say, well, look, it's just two different ways to look at things. There is a connotation associated to the term ether, but really it exists in a sense that it's very similar to what we usually don't call ether. I mean, yeah. Anyway,
and I mean,
but I agree with what you said. Yeah,
there's a sort of like, I don't know, there's a kind of meta-ontological debate here about like whether we should be happy with that kind of thing. If you are happy to just say, well, look, you know, as long as the ether existing in this sense is acceptable, then we can you know, say that the ether exists, then that's fine. In fact, like one of the epicycles I didn't go through has to do with the counterfactual stuff, because you can sort of keep messing around with the counterfactual conditions to get to this point where it looks like when you say the ether exists, you're not actually saying that something that's particularly bad. But there turn out to be other problems with that sort of thing. So I am sympathetic to this idea that maybe when you sort of specify the conditions in sufficient detail, saying that the ether exists is something that we can live with. I think it's kind of, I don't know, one sort of tongue-in-cheek test I have for this sort of thing is like, go and have a chat to a physicist and see if they're going to be happy with that. And I'm not sure that the ether is an entirely comfortable result for some people, but.
All right, David has a finger. Please go ahead.
Very quickly, I was wondering whether, just trying out an idea here, whether there is a tension between your response to Baptiste and also I think the argument in some parts of the talk and your response to Ryan's question and my question earlier, where we were told, you know, we should want to hang on to GR because it's been good to us. You know, and Ryan made the very good point that, you know, so has Newtonian mechanics, and presumably the same is true for ether theory, right? It seems like for a certain time, ether theory was good to us, and we didn't even give it up. We gave it up for very specific reasons. You know, that like even today you could have ether theories that would be empirically equivalent to non-ether theories, and so I'm wondering, if this is the starting, if this is something you take for granted as a starting point for taking approximate functional realization seriously, why we later should be worried by the realizability of the ether roles by the fundamental ontology?
That's a fair question. I mean, I think that there is a difference between the ether case and spacetime in GR. I think that, I think it's got to do with the fact that we've got another theory nearby the ether theory, which is just obviously better, which is the special relativity version, where you get rid of all this added structure. And it's like you can do without it, even at the level of special relativity. And so what I want to say is that like the ether theory is more false than GR is false. And I know that you said false is false, but like I'm enough of a non-classical logician to just think that no, false is not false. There are different kinds of falsity, and maybe GR is false, maybe the ether theory is false, but like finding the ether is still worse because the ether theory is more false. And you know, to put a little bit more flesh on that, I think it's got to do with sort of like meta-theoretic stuff about theory choice. The ether theory is just a sort of ugly, clunky, you know, unparsimonious theory, whereas special relativity is like super slick and streamlined, and that's why I just think that the ether theory is more false than general relativity. But you know, point taken. Like there is a sort of prima facie tension there. Yeah, thanks.
All right, thank you. Enrico has a follow-up.
Yeah, just push again a bit on this point, which seems interesting. So. So you said just now that with the ether theory, you have a very similar theory, which is special relativity, which works better. Now, I was thinking this, isn't that the same with general relativity to some extent, in that, for example, with general relativity, you have things like Regge calculus and things like that, which are very, very similar at the end of the day to general relativity, which from the perspective of the more fundamental quantum gravity theory, such as RQG, are indeed supposed to be better, if you want, in that they are better approximations to the fundamental theory. So isn't that, again, that you have basically the same type of case also in the quantum gravity case that you have for the ether theory again, and just it's the dog biting its tail?
Yeah, I mean, the Reggie calculus is, like, to my mind, not anything like a sort of theory of the scale that general relativity is. It's a sort of procedure for producing solutions to the field equations, that was producing numerical solutions that match the results of churning through the field equations in a way that's more calculationally tractable than churning through the field equations. But it's not like there's a sort of regified version of the field equations has the same status of general relativity. I mean, people have tried. I think people have tried to produce sort of discrete versions of the field equations, but of course it's difficult, right? The field equations are, like the bits of differential geometry, and it's hard to do that on anything other than a continuous manifold, right? So I guess I resist the idea that there is a theory that's like the GR case that's discrete, that is fully satisfied in the case of quantum gravity. I think it would be nice if we could build that.
All right, thank you very much. The next question's by Lorenzo. Please go ahead. Lorenzo Cocco, that is.
Yes, I'd like to begin by saying that I really enjoyed the talk, as this might not be apparent from the way I ask questions usually. I have a suggestion, but before that, which is based on a preliminary question I would like to clarify. Can you please go back to the slide in which you introduce the Ramsification of GR? Yeah, one of the very first ones.
Sure. Yep.
Good. Well, proposed Ramsey sentence, that box. I'm not sure exactly how, well, maybe a first thing is that I assume this is not all of GR because there is nothing about matter right here.
Absolutely, so, yeah. I left the matter field out because it scares me.
Right, but I assume you already anticipated that, so it's not really my point. My question is rather, how does that differ? I'm not sure I understand how does that differ from GR. So how the Ramsey sentence differs from, say, if I try to just write down GR, because you're not Ramsifying over the mathematical stuff, either the manifold or the metric tensor. So I assume that it is all going on in the definition of isometric. Is that right?
Yeah. I mean, like, you're right that I'm not Ramsifying like the field equations. I wouldn't have the first clue about how to do that, and I don't think it would be that useful necessarily anyway for the space-time functionalist. This is supposed to be, and this is supposed to be a fragment of a sort of Ramsey sentence for the theory, but it's what we might think of as space-time in the context of that theory. So it's just the Ramsification of that particular notion in the context of that theory.
Okay, well, we'll do it, Sam. But I assume that if I expand the definition of isometric, I will have something like, well, I have the interval between points, and I have a function which sends the x-axis into the points of the manifold. So that is the stuff we are Ramsifying. So the n tuples will be the function f, and like the distance or the interval. Well, look, maybe I'm cheating a little bit, but the n-tuple is going to be some things that can be represented in that way. So the n-tuple is going to be a set of things that stand in a bijective function into a manifold with this metric structure. Okay. Well, so maybe okay. So take whatever goes into the definition of isometric, maybe congruence. I'm not sure what relation, but whatever we are really Ramsifying over. Yeah. So at least metric structure. Yeah. Something like that. So my suggestion would be, I don't know if this is going to be useful, but this is how I think about it, how I would try to implement inside the project you describe at the end. Because it seems to me that what you're proposing is, let's not take GR, but let's take another theory that says things about location. So what about the following? Suppose we started from, not from GR, but from something a little bit richer. Say you specify that the space-time, the metric is, say, the Schwarzschild metric. And then you describe approximately all the positions or the trajectories of, say, the planets in the solar system, of the sun and the planets in the solar system. And then you took as your theory all the consequences of that about, say, the space-time interval between the pieces of trajectory of the planets. And then you try to Ramsify that. What would you think if we took that as the theory we want to functionalize?
It's an interesting proposal on the face of it. What do I think? So, I mean, just to take a step back to tell you what I was thinking about the location theory, and then see how it sort of aligns with what you're saying. The way I was thinking about the location theory is it might be more like a folk theory. And this part of the reason I think that is because this notion of empirical coherence is almost a kind of pre-scientific concept. It's sort of something that you have to have in your toolbox in order to come to science, to start confirming theories. And it's not obvious that like it's going to be based on a scientific theory itself, depending a little bit on what empirical coherence or empirical confirmation ultimately is. So I was thinking, and I don't think it's like totally just a folk theory, but I was thinking not necessarily like anything like GR that we would be functionalizing. Your suggestion, I think, feels a little bit like, if you had a kind of relationalist type picture almost, right? And you just sort of like take all of the stuff and like treat location as, this sort of relational structure between stuff. And then you go looking to see if anything has a kind of relational structure between stuff of the right kind. I think that's an interesting suggestion. I don't have much to say about it off the top of my head. I think it could be potentially one way to implement this idea of functionalizing location. Yeah, I need to think about it more though. Thanks.
Okay, great, thank you. Claudio has a suggestion. Please, Claudio.
Yeah, thank you. So first of all, thank you so much, Sam, because so I actually took a screenshot and sent it to Fabrice Correa because we're trying to work on a book on a theories of location. So it made me feel useful, actually.
Excellent.
And so I needed it today. So thank you so much. I really needed it today. So here's a suggestion. I think that in the literature on theory of location, we're kind of, let's say neglected things that you might want to take a look at. So for example, there's an old, I can't think of the exact references on the top of my head, but I'll write you. So there's a whole paper by Peter Simons that actually argues that location is a formal concept. So it applies, it doesn't have any restriction whatsoever. And then he actually asks the questions of what minimal structure you have to put in the second slot, to get an interesting theory of location is so there is all these kind of questions in the theory of location, and it's not and now there is an entire literature on what are the kinds of relation, what kinds of relata that goes into, and it doesn't have to be space-time on the right. As a matter of fact, we found proposals that events are located at participants, or properties are located at objects, and so on and so forth. My gut feeling reading the literature is that the minimal that you need is mereological structure to be able to talk, for example, to be able to rule out something like, if I'm entirely located in this room, then I'm not even weakly located at the complement of this room, the mereological complement. So, but it's really weak. So there are, I think, suggestions in the literature on theories of location that will go, hand in hand what you're trying to do, and it's I'm sorry I can't think of that particular paper because that's the most the closest thing I can think of. But I'll go back to my manuscript and get back to you. So yeah, that was just a stupid suggestion.
That would be super useful. And like the sort of stuff on location that I'm familiar with is in Mereology, right? It's all to do with mereological harmony and all that kind of stuff. And, you know, of course, as you pointed out, notions of location are often defined in terms of mereological concepts like mereological overlap and things like that. So yeah, I'd be super interested to see what you guys are doing at any rate. The one thing that, you know, this is just riffing off your suggestion, I suppose, one thing that I've, you know, been interested in is the way that people talk about location without reference to anything like space or time. And I think that people do this in a like totally not metaphorical way when they say things like, you know, the number 2 is a certain node located in a structure. I think that that's not at all metaphorical. I think they literally mean location. Or when people talk about, you know, mathematical objects being located outside of space and time, I think that's also not metaphorical. I think they really do think in terms of location, albeit not spatiotemporal location. And so, you know, one of the things that we might need from these theories is a notion of location that's not spatial or temporal. And maybe thinking harder about location can sort of get us there. But yeah, that's just to say I'm interested in what you're interested in.
Yeah. So just Shapiro, Shapiro really says that, and I really think he means like location. 2 is located in the structure, yeah. And Peter Simons in that paper I told you, like is really actually taking on that. So I will send it to you. And and you probably will know him very well. So Anthony Eagle, for example, replied to a paper that to some discussion that we had, saying because his theory of location doesn't allow, for example, multi-location and nested regions. Like you cannot be multi-located at the region and the proper subregion. And it seemed for universals, and he's straightforward. He said, no, that theory of you shouldn't think of locations of universals, for example, as located at space-time regions. Is really located at different objects. So the second argument place is really objects. And he thinks that that's what Aristotle actually really thought at the beginning. So there are all these kinds, which will be really interesting, I think, for you. And yes.
Yeah, and I think that dovetails with this, sorry, I've lost my name list. So I think it was Lorenzo's suggestion to do something sort of relationalist, right? Where you sort of think of, the problem of empirical coherence and the way that we're sort of thinking about location here is to kind of have a location first picture where you sort of have locations and then you pin objects to those locations. And it's like, okay, well, if we don't have the sort of pin cushion, how can we pin anything to it? But you can reverse that relationship. And there's a sort of long history of reversing that relationship and, starting with the pins and just like getting the cushion out of them. And that seems to be in line with some of the things you're saying, I think.
Excellent. Thank you very much. So we actually have about 5 minutes left, and I'm imposing myself as chair to ask a question now. So first of all, I would like to say that this is, the way you're going with this, I think is very much the direction that Vincent, Nick, and myself are certainly also thinking. So you're quite right that this is the direction we would like to go as well. Now, the reason is not just that it's difficult to functionalize GR or relativistic spacetime, but we also think it's unnecessary because there's a sense in which, despite all of its empirical success, GR imposes a lot of unnecessary structure. It's way more detailed. It contains, in some sense, way more information, in particular in the form of the continuum, that we see absolutely no need to recover in order to fully explain and account for all its empirical successes. So really what we're trying to functionalize when we say space-time functionalism, and this sounds much better than relative location functionalism or something like this. So when we're thinking about this, then it's exactly the relational structure or relative location. Maybe it's also metric things like some distances or at least some sort of coarse-grained distances, durations, relations like this that we will need to have to be able to recover. So when we say we want to functionalize spacetime, we don't want to think too closely of GR, but instead of having spacetime roles like this, what we think at the end of the day will be needed, not just for empirical coherence, but to show that GR is empirically faithful and to make empirical predictions from the theory itself. It's only those things which will have to be recovered, which in a way is I think a much more realistic and much easier task. Not just for the reasons you outlined, but it's extremely difficult to try and get, and basically impossible to show that from the fundamental structures you're gonna approximate in some sense to be made precise a relativistic spacetime. It's a very difficult task, and as I would think, ultimately unnecessary. Anyway, that's a bit of a sort of a brief summary of my reaction.
No, that's really helpful. So I mean, I agree that it's unnecessary. I guess the way that people have been writing about space-time functionalism, because of that name, maybe I've just been confused in virtue of the name, that it's space-time that's at stake. But I think that makes things really hard, actually. And when you talk about space-time emergence, trying to get space-time out of something that's not space-time, it's super hard, like even just to sort of metaphysically comprehend what's going on. But if you break the project down to these little things like location, like distance, contiguity, and I'm inclined to think sort of like some modal structure maybe as well, like the capacity to intervene on parts of the world, in order to sort of like get a picture of empirical observation, then I think that those things are easier to look for rather than this big piece of mathematical structure.
Yeah, I completely agree. No, I think we've been very cagey about this in some sense, and not nowhere nearly as explicit as we should have been. Also because we thought this is a really hard problem, and we're not sure exactly what we should be saying. But I think the direction you're going is absolutely the right one, and there remains a lot of work to be done to say much more precisely and rigorously what exactly it is that we're aiming at. And the book, the forthcoming book with Nick, I hope will contain more towards that sort of goal of the research program.
Yeah, I've been looking forward to that book, which seems to have been
me too.
It's been, I think bits and pieces have been trickling out, but yeah, looking forward to it.
All right. This is great. Thank you very, very much. Everybody, please join me in thanking Sam again.
And thanks everybody for your questions and comments. It was really helpful.